Dear students, Physics Practical Classes ਦੀ ਇੱਕ ਹੋਰ ਸੀਰੀਜ਼ ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। ਅਸੀਂ ਅੱਜ ਦੋ ਨਵੇਂ ਐਕਸਪੈਰੀਮੈਂਟਸ ਲੈ ਕੇ ਤੁਹਾਡੇ ਕੋਲ ਹਾਜ਼ਰ ਹੋਏ ਹਾਂ। ਇਹ ਦੋਵੇਂ ਹੀ ਐਕਸਪੈਰੀਮੈਂਟਸ ਕਿਸੇ ਗਿਵਨ ਵਾਇਰ ਲਈ ਫ੍ਰੀਕੁਐਂਸੀ ਅਤੇ ਲੈਂਥ ਵਿਚਕਾਰ ਰਿਲੇਸ਼ਨ ਨਾਲ ਸੰਬੰਧਿਤ ਹਨ। ਹਾਂ, ਦੋਨੋਂ ਕੇਸਿਸ ਵਿੱਚ ਕੰਡੀਸ਼ਨਸ ਬੇਸ਼ੱਕ ਵੱਖਰੀਆਂ ਹਨ। ਫਰਸਟਲੀ ਅਸੀਂ ਕਾਂਸਟੈਂਟ ਟੈਂਸ਼ਨ ਲਈ ਕੰਮ ਕਰਾਂਗੇ ਅਤੇ ਫਿਰ ਕਾਂਸਟੈਂਟ ਫ੍ਰੀਕੁਐਂਸੀ ਲਈ। ਇਸ ਤਰ੍ਹਾਂ ਫਰਸਟ ਐਕਸਪੈਰੀਮੈਂਟ ਦਾ ਆਬਜੈਕਟਿਵ ਹੈ to study the relation between length of a given wire and tension for a constant frequency using a sonometer. This second experiment the objective है to study the relation between frequency and length of a given wire under constant tension using a sonometer. चलो सब तो पहला ਤੁਹਾਨੂੰ ਇਹ ਦੱਸੀਏ what is a sonometer? A sonometer is an apparatus made of hollow wooden box having two holes. A string is attached to it by which the transverse vibrations of strings can be studied. It is also called the monochord just because it often has only one string. There are two fixed bridges on the wooden rectangular box near its ends, and also there is a pulley at one of its ends. A string is fastened at one end, run over the bridges and the pulley, and attached to a weight holder hanging below the pulley. The string used for this purpose is most often a steel wire. Weights can be added to or removed from the holder in order to increase or decrease tension in the wire. A sonometer demonstrates the relationship between the frequency of the sound produced by a plugged string and the tension, length and mass per unit length of the string. These relationships are usually called Mersenne laws after Marin Mersenne, who investigated and explained them. He found that for small amplitude vibrations, the frequency is proportional to the square root of the tension of the string. Thus, n is proportional to under root t, where n represents the frequency and t represents the tension. This is also known as the law of tension. The reciprocal of the square root of the mass per unit length of the string. Hence, n is proportional to under root of 1 upon m, where m is the linear density of the string. This is known as the law of mass. The reciprocal of the length of the string. Hence, n is proportional to 1 upon L, where L is of course the length of the string. This is known as the law of length. So, आज ਅਸੀਂ ਇੱਕ stretched string ਲਈ ਇਹਨਾਂ factors ਦੇ ਇੱਕ ਦੂਜੇ ਨਾਲ relation experimentally determine ਕਰਾਂਗੇ। ਇਹ ਤਾਂ ਸੀ ਸਾਡੇ main apparatus ਬਾਰੇ ਜਾਣਕਾਰੀ। ਹੁਣ ਜ਼ਰਾ string ਦੀ tension ਨਾਲ related physics ਦੇ ਬਾਰੇ ਵੀ ਜਾਣ ਲਈਏ। for waves on a string, the restoring force is provided by the tension T in the string. The inertial property in this case is the linear mass density rho, which is mass m of the string divided by its length L. Practically speaking, it is the amount of tension in the stretched strings of string instruments, which help them decide the exact frequency of the sound produced. While tuning a string instrument, the amount of tension is increased by tightening it in order to produce a sound of higher note. Similarly, if a particular string is expected to produce a sound of lower note, the tension in this particular string is decreased by loosening it. This practical situation is self-explanatory of the tension and frequency relationship. Let me now also remind you of the nature of different types of vibrations. The first type is free vibrations. Vibrations of a vibrating body continued by itself are called free vibrations. In this case, the body vibrates with its own frequency, called natural frequency. For example, in the Sonometer experiment, vibrations of tuning fork are free vibrations. Then, the second type of vibrations is forced vibrations. Vibrations of a vibrating body under a periodic force are called forced vibrations. In this case, the body vibrates with the frequency of the applied periodic force and only so long as the force acts. Once the periodic force is withdrawn, the body either stops vibrating or vibrates with its own frequency. For example, in Sonometer experiment, vibrations of Sonometer board are forced vibrations. The third type of vibrations is the resonant vibrations. Vibrations of a vibrating body under the influence of a second vibrating body of same frequency kept near it are called resonant vibrations. The phenomenon is called resonance. In this case, the first vibrating body will continue vibrating even when the second body is removed. For example, in the Sonometer experiment, when the paper rider falls, the vibrations of Sonometer wire are resonant vibrations, whereas the wire is in resonance with the tuning fork. Both have same frequency. And now get ready to know the experiments.
The aim of the first part of the experiment is to study the relation between length of a given wire and tension for a constant frequency using a sonometer. Let's see what apparatus we will need to do this experiment. A sonometer along with a hanger and slotted weights, a tuning fork, a half-meter rod, a rubber tablet, and a screw gauge.
Then, it is also important to understand the theory of the said experiment. Suppose a stretched string vibrate in resonance with a tuning fork of frequency n. Then the frequency of vibrating string n is equal to 1 by 2L into under root of capital T by M. Let this be equation 1. Here L is the length of the string, T is the tension in it, and M is its mass. Now for a given string of a fixed mass M, which may be stretched under a given load T, we can write N is proportional to 1 by L, which simply implies that N into L is a constant. Also, using equation 1, we can conclude that if the frequency N is constant, then L upon under root T is a constant. That is, L is equal to a constant into under root T. For constant N, this leads us to the fact that L is proportional to under root T, or L square is proportional to T. There is one more method of expressing the frequency of a vibrating string. Well, it can be expressed as N is equal to 1 by L into D into under root of capital T upon pi rho, where rho is the density of the material of the string and D is its diameter. Now, obviously, for a string of a given material, rho is fixed, stretched under same load T and vibrating in resonance with a tuning fork of given frequency N. We can write rho L into D is equal to a constant. I hope that the theory is clear to you all. Let me now explain the procedure of this experiment.
ਸਭ ਤੋਂ ਪਹਿਲਾਂ ਇੱਥੇ ਦਿਖਾਏ ਅਨੁਸਾਰ ਸੋਨੋਮੀਟਰ ਨੂੰ ਟੇਬਲ ਦੇ ਉੱਤੇ ਰੱਖੋ। ਹੁਣ ਇਹ ਇਨਸ਼ੋਰ ਕਰੋ ਕਿ ਜਿੱਥੇ ਤੱਕ ਹੋ ਸਕੇ ਪੁਲੀ ਫ੍ਰਿਕਸ਼ਨਲੈਸ ਹੋਵੇ। ਹੁਣ ਹੈਂਗਰ ਦੇ ਉੱਤੇ ਇੱਕ ਸੁਟੇਬਲ ਲੋਡ ਰੱਖ ਕੇ ਵਾਇਰ ਨੂੰ ਸਟ੍ਰੈਚ ਕਰੋ। ਇੱਥੇ ਜਿਹੜਾ ਲੋਡ ਅਸੀਂ ਯੂਜ਼ ਕੀਤਾ ਹੈ ਉਸ ਦੀ ਵੈਲਿਊ ਹੈ 19.6 ਨਿਊਟਨ। ਫਿਰ ਇੱਕ ਹਲਕੇ ਜਿਹੇ ਪੇਪਰ ਦੀ ਇੱਕ ਪਤਲੀ ਜਿਹੀ ਸਟ੍ਰਿਪ ਕੱਟੋ ਅਤੇ ਉਸ ਨੂੰ ਅੱਧ ਵਿੱਚੋਂ ਮੋੜ ਕੇ ਅੰਗਰੇਜ਼ੀ ਦੇ ਅੱਖਰ V ਦੀ ਸ਼ੇਪ ਦੇ ਦਿਓ। ਇਸ ਪੇਪਰ ਸਟ੍ਰਿਪ ਨੂੰ ਅਸੀਂ ਰਾਈਡਰ ਬਣਾ ਕੇ ਦੋਨੋਂ ਵੈਜਸ ਦੇ ਵਿਚਕਾਰ ਵਾਇਰ ਦੇ ਉੱਤੇ ਰੱਖਾਂਗੇ। ਹੁਣ ਟਿਊਨਿੰਗ ਫੋਕ ਨੂੰ ਰਬਰ ਟੈਬਲੇਟ ਨਾਲ ਸਟ੍ਰਾਈਕ ਕਰਾਂਗੇ ਅਤੇ ਇਸ ਦੇ ਸਟੈਮ ਨੂੰ ਹੌਲੀ ਜਿਹੇ ਸੋਨੋਮੀਟਰ ਬੋਰਡ ਦੇ ਉੱਤੇ ਰੱਖਾਂਗੇ। ਦੋਨੋਂ ਵੈਜਸ ਵਿਚਲੀ ਲੈਂਥ ਹੌਲੀ-ਹੌਲੀ ਐਡਜਸਟ ਕਰੋ। ਕਿਸੇ ਇੱਕ ਖਾਸ ਐਡਜਸਟਮੈਂਟ ਤੇ ਤੁਸੀਂ ਦੇਖੋਗੇ ਕਿ ਰਾਈਡਰ ਵਾਇਰ ਤੋਂ ਫਲਾਈ ਆਫ ਕਰ ਜਾਂਦਾ ਹੈ। ਦੋਨੋਂ ਵੈਜਸ ਵਿਚਲੀ ਇਹੀ ਲੈਂਥ ਰੈਜ਼ੋਨੈਂਟ ਲੈਂਥ ਕਹਾਉਂਦੀ ਹੈ। Measure the resonant length with the help of meter rod. For the example set here, it is found to be 35 centimeter. Now add a load of 0.5 kilogram weight to the hanger and find the resonant length twice for this load using the same tuning fork. The load now has become 24.6 Newton. Take 3 more loads and go on increasing the load every time and find the resonant length each time. Then increase the load in small steps and take 3 sets corresponding to each of the different loads. Find the corresponding resonant lengths, keeping load fixed, just as you did earlier. Record your observations like this. Frequency of the tuning fork, nu, is equal to 480 Hz. This is the desired observation table. Have a careful look at the readings noted here. There aren't much of calculations. Just plot a graph between L square and T. Take T along y-axis and L square along x-axis, as you can see here. As you plot the corresponding points and join them, the graph must appear as a straight line. The declaration of the result is to be made like this. As graph between L square and T is a straight line, L square upon T is a constant. And now it is the turn to learn the precautions that we are supposed to follow for this particular experiment. Let's know what are these. The area of cross-section of the wire should be uniform. Loading of wire should be within elastic limit. Pulley should be frictionless. Despite following all precautions, certain errors always creep in. These sources of error are: string may not be of uniform area of cross-section, string may not be rigid.
ਆਸ ਹੈ ਕਿ ਇਹ ਐਕਸਪੈਰੀਮੈਂਟ ਤੁਹਾਨੂੰ ਸਾਰਿਆਂ ਨੂੰ ਇੰਟਰਸਟਿੰਗ ਲੱਗਿਆ ਹੋਵੇਗਾ। ਤੁਹਾਨੂੰ ਯਾਦ ਹੀ ਹੋਵੇਗਾ ਕਿ ਅਸੀਂ ਇੱਕ ਹੋਰ ਵੀ ਐਕਸਪੈਰੀਮੈਂਟ ਕਰਨਾ ਹੈ। ਅੱਜ ਦਾ ਸੈਕੰਡ ਐਕਸਪੈਰੀਮੈਂਟ ਵੀ ਸੋਨੋਮੀਟਰ ਦੀ ਹੀ ਹੈਲਪ ਨਾਲ ਕਰਾਂਗੇ। ਇਸ ਵਿੱਚ ਅਸੀਂ ਇੱਕ ਕਨਸਟੈਂਟ ਟੈਂਸ਼ਨ ਲਈ ਇੱਕ ਗਿਵਨ ਵਾਇਰ ਦੀ ਫ੍ਰੀਕੁਐਂਸੀ ਐਂਡ ਲੈਂਥ ਵਿਚਕਾਰ ਰਿਲੇਸ਼ਨ एस्टैब्लिश करांगे। चलो आज दा सेकंड एक्सपेरिमेंट देखिए।
इस एक्सपेरिमेंट दा एम है to study the relation between frequency and length of a given wire under constant tension using a sonometer. Apparatus काफी कुछ फर्स्ट एक्सपेरिमेंट वाला ही है। आओ देखिए। A sonometer along with a hanger and slotted weights, tuning forks of different frequencies, a half-meter rod, a rubber tablet, and a screw gauge.
It is important to understand the theory or theoretical explanation of every experiment that we perform. In this case, it is just the same as we studied for the first experiment. I'll just brush the relevant part for the sake of completion of the experiment. Suppose a stretched string vibrate in resonance with a tuning fork of frequency n. Then the frequency of vibrating string n is equal to 1 by 2L into under root of capital T by M. Here L is the length of the string, T is the tension in it, and M is its mass. Now, for a given string of a fixed mass M, which may be stretched under the given load T, we can write N is proportional to 1 by L, which simply means that N into L is a constant. I believe that you are all now ready to know the procedure of this experiment.
Procedure. To start with the procedure, place the sonometer on a table as you can see here. You must make sure that the pulley does not have friction. Now, stretch the wire by putting a suitable load on the hanger. In the present setup, a load of 19.6 Newton has been used. Next, cut a small and light paper strip. Give it a fold at its center to give it a V shape. Use this as a rider by placing it at the middle of the wire between the two wedges. Now, strike the tuning fork against the rubber tablet and place its stem on the sonometer board. Adjust the length between the wedges very slowly so that at a particular adjustment you find that the rider flies away from the wire. This length between the wedges is the resonant length. Measure the resonant length with the help of meter rod. As you can see, for the example set here, it is measured to be 35 centimeter. As the next step, add a load of 0.5 kilogram weight to the hanger and find the resonant length twice for this load using the same tuning fork. The load has now become 24.6 Newton. Take 3 more loads and go on increasing the load every time and find the corresponding resonant length each time. Then increase the load in small steps and take 3 sets corresponding to different loads. Find the corresponding resonant lengths, keeping load fixed just as you did earlier. You can now use the second and then the third tuning fork as well and follow the same procedure. Record these observations in your notebook. Mass of hanger is equal to 0.5 kilogram. Weight of hanger is equal to 0.5 into 9.8 is equal to 4.9 Newton. Mass of each slotted weight is equal to 0.5 kilogram. Fixed value of load used is equal to 0.5 plus 0.5 into 3, which is equal to 2.0 kilogram. Hence, constant tension used is equal to 2.0 into 9.8 is equal to 19.6 Newton. And then the observation table is to be made like this. Watch the observations carefully. In the name of calculations, we plot a graph between the frequency n and 1 by L. The frequency n is to be taken along x-axis and 1 by L along y-axis. The same you can observe here. The graph is a straight line. Let's see how to put forward the result. As the graph between n and 1 by L is straight line, n is proportional to 1 by L, or n into L is a constant. The precautions that we are expected to abide by are: the area of cross-section of the wire should be uniform, loading of wire should be within elastic limit, pulley should be frictionless. The easiest to affect sources of error are: wire may not be of uniform area of cross-section, wire may not be rigid, pulley may not be frictionless.
Students, now I am going to introduce some questions suitable for viva of these experiments. My first question is, what is a sonometer? The answer to this question is, a sonometer is an apparatus made of hollow wooden box having two holes and a string attached to it. The next question is, why are there two holes on the sides of the sonometer? The answer is, to make air vibrating inside the box to come in contact of outside air to enhance vibrations. The next question asks, what is the nature of vibrations of the tuning fork? The answer, the vibrations of the tuning fork are free vibrations. ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਸੀਂ ਅੱਜ ਸਿਖਾਏ ਗਏ ਦੋਨੋਂ ਐਕਸਪੈਰੀਮੈਂਟਸ ਨੂੰ ਪੂਰੀ ਤਰ੍ਹਾਂ ਸਮਝਿਆ ਹੋਣਾ ਹੈ ਅਤੇ ਇਹ ਤੁਹਾਨੂੰ ਇੰਟਰਸਟਿੰਗ ਵੀ ਲੱਗੇ ਹੋਣਗੇ। ਆਸ ਹੈ ਕਿ ਅੱਜ ਪੁੱਛੇ ਗਏ ਸਾਰੇ ਕੁਐਸਚਨਸ ਦੇ ਆਨਸਰਸ ਤੁਹਾਨੂੰ ਪਹਿਲਾਂ ਹੀ ਆਉਂਦੇ ਹੋਣਗੇ। ਅੱਜ ਦੇ ਲੈਸਨ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਤੁਹਾਡਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਵਿੱਚ ਹੋਰ ਨਵੇਂ ਟੌਪਿਕਸ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। ਤਦ ਤੱਕ ਟੇਕ ਕੇਅਰ, ਸਟੱਡੀ ਵੈਲ ਐਂਡ Enjoy yourselves.